Let's look at the effect of that angle of attack. So let's draw our rectangular object again. Let's draw it with a very small angle of attack here, and let's draw it with a really big angle of attack here. So I'm going to draw that rectangular object, and of course we're going to start relating this to a different shape later on where it's going to be the profile of a wind turbine blade. That's where we're going with this. Same physics is going to also apply to water power across sort of the fins and veins of water turbines. It's just a different fluid, water instead of air. So here's a small angle of attack alpha, small angle of attack, and here's a large angle of attack alpha. So I want to look at what happens to the lift force and the drag force if, again, we have wind coming in from the same direction. And I'm going to show wind as velocity v now. So what happens here when there's a small angle of attack, the component in the upwards direction, the component in the y direction, which is your lift force, is large. But the component in the x direction, which is your drag force, is small. We haven't talked yet about what's better, a lift force or a drag force, but you can make your guesses right now in terms of the effect of the torque. What do you want? Small lift, large lift, or large drag force on a wind turbine? But you see here that if it is just a rectangular shaped object, then there's a very different ratio between lift and drag force that is entirely dependent on the angle of attack. So the drag force is very large with a large angle of attack, but the lift force is small with a large angle of attack. That's for this rectangular shaped object. Where I'm going with this is we actually try to maximize lift force, and because of that, a rectangular shape is not an ideal profile to optimize the lift force through all angles of attack, because as you can see, it changes.